a reasonable model for a good number of applications of electromagnetic waves. We call such a situation a plane wave. Perhaps obviously because the electric and magnetic fields are oriented along the surface of a plane consistently. There are other propagation geometries. We could imagine a spherical propagation from a point radially away from the point in all directions. Having that discussion requires adapting all of our calculus for spherical coordinates, which I'd like to leave just outside the scope of our course. There's a little bit left in our discussion of even this relatively, no pun intended, relatively straightforward propagation of electromagnetic waves. Back in 231, when we talked about, well, we might not have talked about it in 231, but back last week, when we talked about mechanical waves. If we think about a wave propagating along a string, the string moves perpendicular to the direction of transfer. The material that is doing the communicating doesn't actually move from place to place, but the energy does, right? We can transmit the oscillation, the energy associated with oscillation along the medium from one point in space to another. Here, we don't even have a physical medium, although I suppose we could. But it's not the medium that's doing the propagation. It is, in fact, the electric and magnetic fields themselves. The medium through which they propagate might be relevant because we know if we change the medium, we might be changing the permit and permeability, permittivity and permeability of that space, which might change the relative strengths of these fields and say something about the propagation. Maybe it changes the looking down at our conclusions. Maybe it changes something about the speed with which the wave propagates through that particular medium, if we change either the permeability or the permittivity or both. So the point of the wave still, though, if this is, and it is, a wave that is propagating through vacuum or through a medium, the fundamental truth of a wave is that it transfers energy. There are two related concerns with that. Two things I really kind of want to know. I want to talk about the direction that we're sending this energy. And since we have a dimensionality to this problem, this situation we considered, right? We've got fields that oscillate in the YZ plane, but changing along the x-axis. Everything we wrote was partial x, partial x, partial x. We didn't consider any variation with changing y or z coordinates. We assumed everything was uniform along the YZ plane. So if we can sort of lean on our analogy of a wave oscillating on a string, propagating along a string, we can think about I guess it makes me hope that the direction of energy propagation is along the x-axis. And I'd also like to know exactly what is the rate at which we're transferring energy this way. What's the power associated with this thing? We ask the same question about a mechanical wave. We could ask it about this one as well. So, with that, let's pick up where we left off. Close propagation, yes. I'm hesitating a little bit because there's a fact that I'd like to grab, but whose accuracy depends on a completely separate but analogous construction of an electromagnetic plane wave, a different derivation. And I'm tempted to grab this relationship from an entirely separate circumstance. But I don't think I think I have to start from it and ask you to ascertain the truth of it in your own work, in the interest of time. We have said Tuesday, that the electric field associated with that planar orientation that we considered was in fact describable by a wave equation such that, and I want to make sure that the notation is the same. So I want to go grab that notation for real. We wrote that E sub y is a function of x and time that satisfies the wave equation. If it satisfies the wave equation, we have its solution ready at hand. We know that it has some amplitude and that it is describable this way. This is a traveling oscillation, an oscillation traveling in the positive x direction, exactly as we have assumed. We know also that if we had used the reverse partial derivatives, if we had flipped them, we would have said that the z component is also a function that satisfies the wave equation and so is describable with an amplitude and a traveling cosine representation. We might be tempted to write these as the vector equations that they are. Our assumptions for this plane wave propagating along the x-axis are that the electric field is only in the y direction. And that the magnetic field is only in the z direction. Note that these two k's have very little to do with each other. That one signifies the z direction. This one has to do with the spatial period of the propagation, how much space along the x-axis is required for one full oscillation of the magnetic field. These are entirely different questions, measured on, in fact, perpendicular directions. In which direction is the cross product? The magnitude of 1 times the magnitude of the other times the sine of the angle between them, but they are in fact perpendicular in a direction according to the right-hand rule. What is J cross K?
I think it's I.
It is, yeah. The directions of the various cross products obey a kind of Pac-Man logic. They wrap from right to left, and then if you walk off the right-hand side of the screen, you end up on the other side. So as long as we put them in alphabetical order, I, J, K, at whichever one we start, we move or through alphabetically around the other side. So K, I, K cross I equals J, because that's the next thing. J cross K equals I. And that all has to do with the right-handed coordinate system that we set up. Yep. It is, I don't think, a coincidence that this is the direction of propagation. How do the amplitudes compare? It's just, I'm like physically opposed. Like I don't want to do it. I want to go prove it, but I also want to make sure we get to what we need to say today. I gotta say a little bit more. How is this a real thing? Can I really quickly justify this? Does this even work? Like dimensionally? Is a volt per meter the same as a meter per second times a Tesla? You know what's interesting? This isn't the first time we've seen this equation. Back when we were talking about cross-oriented electric and magnetic fields, talking about a velocity selector, we had a situation where there were capacitor plates and a magnetic field into the board. And we were interested in the speed with which a charged particle could pass undeflected. Well, undeflected means that the net force is zero, which means the electric force and the magnetic force are the same. They cancel each other out because we can't get away from the electric force between those two charged plates. We know that there is one, which means we have to cancel it with the magnetic force. And if we cancel the charge of that particle, we have actually already seen that the electric field has the dimensionality of speed times magnetic field. So there is no charged particle here, but there is some energy propagating with a speed through vacuum of 1 over the square root of mu epsilon. So yeah, I mean, I guess I can make a sort of a low rigor argument that the propagation direction doesn't change as long as this is true. Because that's an undeflected charged particle. So as long as we've got a plane wave, then the magnitudes have to be related this way. The speed of propagation and it's a low rigor. I admit. These were static electric fields, magnetic fields that were set up in a region. These are the oscillating electric and magnetic fields that are actually coming with us. They're oscillating as we go, but I think it's enough of a justification that I can leave it here and point you to the resources you have for further reading. So that means we can rewrite this. Or as that. If you're thinking about different things that we've seen along the way, like how the average power dissipated by a resistor in a driven RLC circuit, an AC circuit, needed the square, half the square of the cosine, right? The average value of cosine squared is a half. And we ended up with defining like a root mean square, right? So it's like I max the amplitude of the current times the resistance squared over 2, but that meant that we got like an RMS kind of thing. I'm also thinking about the because I was thinking about energy propagation, right? The energy is moving through space, and I started to think about the energy stored in the electric field between two, capacitor plates. The how did it go? The volumetric energy density. Was that, I think. So I see this E squared over here, and I think about energy, and I see the cosine squared, and I think about power. Which is interesting. More on that in a second. Suppose we aren't in a vacuum. Suppose we are not considering propagation in free space, but in some other space. Such that the velocity, phase velocity, I suppose, with which the one that satisfies the wave equation is in terms of some other permeability and some other permittivity in general, which would be expressible in terms of the relative permeability and the relative permittivity. but 1 over the original permittivity and permeability of free space is the speed of light in a vacuum. So we can sort of track the speed of the propagation in this medium with its permittivity and permeability in terms of well, being relative to the speed of propagation in a vacuum in free space. We might use this quantity, the square root of the relative the relative field generating constants, whichever ones we're talking about. We might use that itself to keep track of how different the speed of propagation is in this medium compared to what it is in free space. To index, just to keep track, the relative speeds. Which we could write as the lowercase letter n. The index of refraction, if you'd like to call it that. We're not entirely sure what that means, but we could define it, sure. What is it for now? The index of relative speed. Let's talk about the energy associated with this propagating disturbance. We know that the total energy per unit volume, the energy density, total stored energy U per unit volume, is in fact and if this is free space, that'll make things a little bit easier. But we just wrote that there's a relationship between the amplitudes. C, the propagation speed in free space, is actually expressed as the reciprocal of the ratio, right? So if we move things to the other side, we end up saying that radical mu epsilon E max is equal to B max. Because C is 1 over square root mu epsilon. So we could, if we wanted to, replace the B magnitude with that thing we just wrote. So if we square the radical, we get a mu, but that's going to cancel the mu in the denominator. We're going to square the epsilon, so we get an epsilon, a single epsilon, and e squared. Oh, neat. I imagine if we had tried this trick the other way, we would also end up saying that it's just and we lose the factor of 2. We want to talk about power, and we want to talk about propagation. Let me go get this picture again. As our plane wave propagates from this x coordinate to this one, there is an amount of energy associated with that propagation. A total amount of energy du, because during our derivation, we let delta x become very, very small. We took the limit. So we're talking about a calculus-sized bit of energy contained in this volume. Which has to do with the energy density in this region between those two planes. And it's okay that we're talking about that because we assumed that this region was small enough as we let delta x go to 0 that E and B were both constant in that region. So we're just talking about a single, like a constant energy density U times the volume represented by that space. How big is that space? Well, it's the area in question, area of this plane, times the distance that we propagate, dx in the limit. Dx, though, is the distance along the x-axis that we have traveling at a speed equal to the speed of propagation in a small amount of time. And we know what little u is equal to. We just wrote it. My metric still depends on the cross-sectional area of this thing that we're considering, which is a little bit awkward. What if we asked about the energy per, well, the energy per area? We talked about, we did a similar trick back when we were talking about current, and then we defined current density, right? Is the sort of cross-sectional current over area, you know? So we could do the same thing here. We could define, well, the rate of energy transfer, du, capital U, dt, is this. And if we wanted that per area, we could write that. And we could define this as a thing. Following the convention, I'm going to call it capital S for now. Based on this expression, it has joules per second per area. Joules per second is watts. Watts per meter squared. This is well, it's power per cross-sectional area. I think we called this intensity. If we didn't, we should have. Now, capital E varies with time. As these fields change, presumably there's a different amount of energy stored in this volume. there's a moment when both the electric and magnetic fields are instantaneously zero, at which moment there is no energy stored in them because neither of them have a magnitude. On average, though, we would go from 0 to this, I guess, this maximum value. But I started out by saying that I was interested in the propagation direction as well. Is there a way all at once to talk about the uh, energy transmission and its direction, like how much and in what direction, all at the same time? In order to talk about direction, we need a vector quantity. But power per area doesn't have a dimension. So we're going to have to like define a new vector quantity that follows this and has a direction. But we did in fact already sort of look into a propagation direction if we ask for the cross product. What about, wait a minute. E cross B is, I guess, one of these three expressions. This one, or this one. We know that it has the right direction. C E cross B is E squared over C. I'm trying to take this idea and stuff it into the cross product somehow, because the cross product has baked in the directionality that we want. I'm going to rewrite it down here so I don't have, I can stop scrolling back and forth. We said that the cross product C No. Was it E? It was E squared over C? Yeah. E squared. If I can use this definition, the circled one, should be this new thing S divided by because this division by C is there, and this one comes from the algebra. So this is C squared C squared times epsilon. Now C is 1 over the square root of, so if we square it, it's mu epsilon. So C squared times epsilon is just 1 over mu. This thing we just defined, the power per unit area, I guess, the instantaneous power per unit area, is really close to the cross product of E and B. It's to within a multiple of mu zero. But that's in the denominator, so we got to put it S times mu zero. But now there's a directionality associated with. So, okay, so wait. What if we define a vector version of that S? In terms of E cross B, but to keep the magnitudes right, S divided by, it's got to be 1 over mu zero. This new definition, 3-line equals. S was not a vector before. We are saying here is a thing that is the vector represented by the symbol S. What do you want to call it? I want to call it the pointing vector, after the scientist that first proposed it. It has a really nice mnemonic device built in. What does it show you? The direction the wave is pointing. It's nice when, you know, names line up like that. E cross B is the direction of propagation. And if we adjust it just a little bit by the permeability of the medium, we are talking about the instantaneous intensity. It's not really intensity, because intensity was never a vector. It's something like intensity. It's directed intensity. With this definition, we can write using a very familiar notation that the power transmitted or transformed by this wave is the net pointing flux through a closed surface. This thing looks like directed power per unit area. So if we take a closed surface for that much area, how much power is being sent through that surface? This much. What is the average value of the pointing vector? It's in the x direction. We have no choice about that. And it has a magnitude according to the magnitude of the cross product that we wrote up here. Let's stay with this one. Which is the average value of Emax Bmax cosine squared kx minus omega t. And what is the average value? I mean, the Emax and Bmax are just constants. We're going to multiply the average anyway. What's the average value of the square of the trig function? It's 1/2. But I'm missing the mu from the definition. This is the cross product magnitude. And then we have to divide by mu. Because of the definition of the pointing vector. And then now that we have discussed the magnitude of the thing, we can say that this is, in fact, the intensity I of an electromagnetic wave is equal to the average magnitude of the pointing vector.